All right, class, we should probably get started. Um, let's start our lecture for today. As always, just a reminder about logistical things that are out there. I hope my screen share is visible. Let me just first fix that. So quick reminder, homework 1 is on Canvas, and you should, it's due in a couple of weeks. It's about decision trees, and in fact, it's just about decision trees. There's really nothing about linear classifiers there. So please do start as soon as you can. At the end of today's lecture, a good part of the homework should be accessible to you. So please, I recommend that you start soon. This homework typically takes a little more time than people estimate at the beginning, simply because this is the homework where you're setting things up and making sure that your code runs and such things. So there's a little bit more logistical stuff that needs to be in place for this homework. And as we go along, the subsequent homeworks will feel easier because you won't be doing the same thing again. So please do start as soon as you can. It's due in a couple of weeks. And for students who are watching this on YouTube, the live stream, and are not yet registered for the class is essentially full. I've handed out permission codes to waitlisted students. I don't think there's anyone else on the waitlist who's expressed interest in being in the class. So if you are, I will just send me an email and I'll go over it. Before we start today's lecture, let's go over some questions, any technical issues that you have, and I see there's already one. There's a question about homework 1. Do we include features for each decision tree, or should you simplify? I suggest I'm assuming this is for the first question where you have to write down trees by hand, and I suggest you just simplify. You don't have to create the smallest possible tree, but make it as small as you can, simply because it will just make it easier to grade. All we want is a tree. We don't need to have every single feature. The important thing is you should have, the tree should be complete in the sense that for any input, I should be able to produce an output, and the tree should be exactly the function that is in the first question, whatever the sub-question is. So you don't need to include features that are irrelevant, if that's the question. There was also a question on Canvas about using scikit-learn to read the data. I'm not entirely sure how I feel about that. To be honest, I feel a little uncomfortable allowing you to use scikit-learn to read the data, simply because this data format is so easy. You can write your own reader. And maybe if it comes down to it, we can even supply you with a reader. The reason I am a little bit hesitant to allow using scikit-learn to read data is because it will make it harder for us to check if scikit-learn is used for something else. Just to remind you, in this class, for the general policy is going to be that any algorithm that we cover in detail in the class, you have to implement on your own. You should not use any machine learning library. Scikit-learn is a popular machine learning library, but if you're going to, I'm sure it's easy for you to see why I'm making that restriction, because if the goal is to not use, if your goal is to learn how the inside of an algorithm works, there's no point in just using the library. And technically, reading data is not that complicated. It's not really machine learning, but it's going to be harder for us to grade and check if scikit-learn is used for something else. There might be some automated scripts that will just confuse us. So I suggest make it easier. Just reading the data format that we have given for this homework will be the format that we will use for all the homeworks. It's called the libsvm format. And it's actually one of the reasons we use this is because it's so easy to read. All you have to do is just white space split each line. So I suggest you don't use scikit-learn. All right. Are there any other logistical things we need to get out of the way before we move on to the main part of the class? Looks like not. So I can see you're all eager to continue with our lecture. So let's jump right back in. In the last lecture, towards the end, we were looking at what decision trees are. And using a bunch of examples and such things, we saw this, but once again, my screen share is stopped, so I'll have to redo this. So we saw that a bunch of examples that talk about what decision trees are using triangles and circles and such things. But at a high level, a decision tree is just a classifier. It's a function. Instances are represented by features, and the way this function is defined is that it's a tree. It's a hierarchical data structure where nodes are testing for does this feature take a certain value, or it could be more complicated tests also. But nodes are essentially tests. So you have nodes, and it has multiple branches, and each branch is a different value that the test can take. And the way the tree is defined, if you go down to the leaf is a label. So you could have another node here, and that's another leaf. So I'm just using circles for tests and squares for the labels in this picture. So it's a hierarchical data structure, and we saw an example involving these triangles and squares, and we saw this decision tree where you could label things. And there was an interesting discussion at the end of the last lecture about what happens if the tree does not even, if the node test fails. So for example here, just to remind you how the prediction works, if I'm asking what's the label for the red triangle, we go down the tree. First, we have what's the color. We ask what's the color, the answer is red, so we go down the red path, and we've reached a leaf, so labels B. If it was a blue triangle, then we'd have gone down this path, and then we see that there's another test for shape. And then we go down this path again, it's a triangle, so the label's a B. At the end of the last lecture, we saw this sort of a strange example where we had a green triangle. So we can again go down this path, green, and suddenly the shape either has a square or a circle. There's no triangle here, so this thing crashes. So this example is kind of a pathological case when really you should have a default label for triangle also, maybe a B. So this is a triangle. So the point of these examples is to show you how easy it is to make predictions with decision trees. All you have to do is just go down the tree and so find the leaf that satisfies all the questions that each node has asked. The next question is, and this is really the new stuff that we are starting today, is what kind of functions do decision trees represent? And this is something that I would encourage you to start thinking about every time we encounter a new class of functions like decision trees. We will encounter linear classifiers, we'll encounter neural networks, and so on. And every time we encounter a new hypothesis class, it's worth asking what functions do they represent? Because once you understand that, or at least characterize that, you might be able to get a sense of, should I use this class of functions for my problem? So when we talk about the expressiveness of decision trees, well, the answer is actually rather simple. Decision trees can represent any Boolean function. And the way to think about that is, let's take this tree here as an example. So when will the label be a B? So the labels will be here, and here. So I can say something like, if color equals blue and shape equals triangle, then, or actually, let me write it this way. So yes, so let me, so if this is the case, then the label is a B, or you have a B here also, right? If color equals red, then the label is a B, or, oh, sorry, not or, this is an and. And if the color is green and the shape is a square, then this label is B. So I have written the tree as a collection of rules. Now, this kind of a thing, I mean, basically, it's not particularly hard to show. If you've seen this before, it's not hard to show. It's not just take my word here. Any Boolean function can be written in this form. This is essentially just a slightly different version of something called a conjunctive normal form. Uh-oh. The conjunctive normal form is just a way of writing a function with a bunch of ands and a whole bunch of ors in between. So there's a clarification question. Won't this always be false because the object cannot be both red and blue and green? Now that's an interesting one. So actually that's not true, because the way this implication works is if the left-hand side is false, then the whole thing becomes true. So if the color is blue, then the color cannot be red, which means this thing is false here, which means the whole thing is true. This is the definition of a logical implication. If the left-hand side of an implication is false, the whole implication is true. This is false, as a result, the whole implication is true. And this is true. And for this to be true, the color has to be blue. Yes, it's an implication function. In any case, so in case you were not particularly fond of my handwriting, this is the cleaner version of this. So you can write the full decision tree as a conjunction of every path in the tree. It's just if the first path is true, the second path is true, and the third path is true, and so on. So this path is really this rule here, and so on. So in this case, then you can write any Boolean function. So this, what I have shown here is, given a tree, convert it into a Boolean function. But you can also do the opposite. For any Boolean function, you can convert it into a decision tree. So this is an important point here. Any Boolean function can be represented as a decision tree. And this is what I'm asking you to do in your homework. So as an exercise, let me just show you an example. So let's consider a Boolean function like, say, f of x is, say, let's say we have two variables, f of x1 and x2. We have two variables is, say, not x1 and x2. So just to kind of help you parse this notation, this is not and this is and. So the truth table for this, I mean, in case you haven't seen this notation for a while, I just want to remind you, this function looks like this. It's an x1, x2, and an f. I'm using 0 for false and 1 for true. These are the only 4 things that you can have. When for this function to be true, when x1 is false and x2 is false, this becomes false because the not x1 is true when x1 is false, and x2 is also false. x2 is false, so the whole thing disappears. Here it's a 1, here it's a 0, and here it's a 0. So if I want to write this as a decision tree, the way to think about this is let's consider the value of x1. X1 can either be, I'm just arbitrarily picking x1 as the root here. X1 can either be true or false. If x1 is true, notice that the function is always false. So I don't even have to go beyond. Otherwise, I consider x2, and x2 can be true or false. If x2 is true, the function is true. If x2 is false, the function is false. So I have this. So I have converted the tree. I have converted the function into a tree. So you can convert any Boolean function into a decision tree. And your homework, the first question, asks you to explore this idea with a few different Boolean functions, just to kind of warm you up to this idea. All right. So there's a question in chat, and Matthias already answered it, and we'll get there in a bit. So decision trees can represent any Boolean function. The next thing to think about is, can they represent other functions? Can they represent functions that are not Boolean? And actually, you can. These are called regression trees. So far, all we have seen, can they represent functions that are not discrete? So far, all the examples we've seen involve classification. The labels are discrete categories. But you can also have real valued categories where the leaf is no longer just a category, but the leaf is a function that produces a number. And depending on the path you take in the tree, you might be choosing a different function. These things are called regression trees. We won't be talking about regression trees a lot. If you're interested and you want to follow up on that, look up CART, classification and regression trees, these are called. And decision trees are really old. I mean, they've been around, we'll see in a bit, they've been around since the 60s, at least in the way we recognize them now. And conceptually, the idea is rather simple. As a result, there's a lot of work on handling noise, handling what to do, what to do when we have missing features, helping with generalization and so on. And we'll talk about a lot of these things as we go along. The next thing to think about is what happens when we have features that are not categorical. All we have seen so far are categorical features, at least in the example. The color is blue, green, or red. What if the color is actually a wavelength? It's a number. The problem with numeric values, or let's say we have length. So there is no hope for me to use length, and for every possible value of length, if I start putting edges out of this node, there will be an infinite number of things. So there's no hope, because length is a real number. So how do we deal with numeric features? And the answer is, one way or another, you essentially discretize them. You bucket them into groups, or you threshold them somehow. And that's what we'll do. For example, if you have this function here, let's say I want to represent this function as a decision tree. The function is plus in this region. I can't stay within the lines clearly. And minus everywhere else. So how do I build a decision tree for that? The answer is, you identify the boundaries. And notice that you can have a threshold here. You can have a threshold here, a threshold here, and a threshold here. So you have a decision tree that looks like this. If x is less than 3, that is essentially this side of this line. If it is less than 3, then you are going down this path. Then you check if y is less than 5, which is below here. If it is going down this path, then you check again if x is less than 1. And if that's the case, it's a minus. And you can discretize this in many different ways. You're essentially, I encourage you to kind of convince yourself that this tree will always give a plus and a minus as per this picture here. So there are a lot of tricks about how to discretize real valued features. If you're interested, we can talk about this offline. The short answer is, you need to do some pre-processing. and there's a question about numeric features. We are assuming that it's uncountable. Yes, we are assuming real numbers basically, or at least some subset of real numbers, an uncountable subset. The important thing here is notice that by choosing these kinds of boundaries, by choosing these kinds of splitting points, I'm creating non-linear decision boundaries. The idea of a decision boundary is something we haven't encountered before. It's something that we will deal with a lot as we go along. Mostly when we talk about linear classifiers and such things, linear classifiers are very well studied. And to the point where there's like a whole bunch of algorithms that were invented essentially for linear classifiers. And it's easy to use, and there's a lot of efficient code for linear classifiers, but life is not necessarily linear. So we need the technology, we need the tools to handle decision boundaries. Decision boundaries are the boundaries between the positive and the negative points. Decision boundaries, we need tools that can handle decision boundaries that are non-linear. Decision trees are an example of classifiers that support non-linear decision boundaries. Of course, these are not the only ones. Multi-layer neural networks can do that. Kernel tricks, the kernels will allow us to do that. If time permits, we'll talk about kernels. And decision trees are the first example of a non-linear classifier that we've seen so far. Very briefly, to wrap up, just this discussion of what decision trees are, we'll talk about how to learn them. A decision tree is a hierarchical representation that can represent any Boolean function. It's a way of, it's a classifier, sure, but it's essentially just a compact way of representing a lot of data, summarizing a lot of data. And if you want to make a prediction with the decision tree, you just go down the decision tree and get to the leaf that answers all the questions. Now, one thing I want you to think about is this really important point at the bottom. Given a data set, there can be many decision trees that represent it. And you should convince yourself this is true. Pick one of the data sets that we've seen so far, or take a data set that we will see afterwards, and convince yourself that there are many decision trees that can represent the exact same data. Even in the tiny example that we saw before, here I chose to have a tree rooted with x1. I could have created another tree with x2 as the root, try to do that, and both of them are perfectly legal trees for this function. So the question then that comes into play is, how do we know which decision tree we should pick? If there are many decision trees that perfectly agree with the data, how do you know which one to pick? And that becomes the crux of the learning question. That's what we'll get to next. A very brief set of exercises so that you can kind of play with this a little bit more. You can do this afterwards, and if you have trouble, you can come to us. You write down the decision tree for this exact data with, we saw the example where color was the root. I want you to write it with shape as the root, and just to kind of build a tree by hand. And then think about whether these two trees will always make the same predictions for examples that were not seen. In fact, try to come up with a tree where these two, an example where these two trees, the one that is rooted with shape and the one that's rooted at color, would disagree with each other. The other thing that I want you to think about is, try to prove that multiple trees that look different, structurally different, can always represent the same Boolean function if you have two or more variables. I kind of gave you a hint of a proof with this, choosing a different root, for example. And to kind of formalize it, you might have to, inductively grow that. You can make an inductive proof. The reason I'm asking you to think about this is I want you to think about what it means when two trees are structurally different. You can have two trees that are structurally different, namely they are different data structures if you're storing them in memory, but they are functionally identical, and this is guaranteed to happen. if you have 2 or more variables. Try to prove it. All right. So this is a good stopping point. Let me see if there are any questions. There aren't any. So I'm going to now move to the question of learning decision trees. So we've seen what decision trees are. The next thing is to learn decision trees. And in particular, we'll spend a fair amount of time looking at this algorithm called ID3. ID3 is short for iterative dichotomizer tree, the third of that family, I guess. And it's a heuristic for building decision trees from data. If time permits, today or maybe Tuesday, we'll look at some extensions of this algorithm to deal with things like noise and missing features and such things. So today, the goal is to spend most of our time with our first learning algorithm. I actually like to talk about the history of these topics a little bit before for every new topic that we see. So decision tree research, as I said before, has been around for a while. And not just in computer science, not just in AI, not just in machine learning, but across multiple disciplines. The algorithm that we'll see today is called ID3, and it was developed by Quinlan. That's his claim to fame. And it played a big role in the 1970s when expert systems were a big deal. Expert systems were essentially rules that were learned from examples. And it used, ID3 specifically uses a information theoretic motivation for developing the, growing the tree. Very soon after that, Leo Breiman, Jerome Friedman, and other colleagues from statistics developed CART, classification and regression trees, which used other kind of heuristics for growing trees. There was an explosion of work around decision trees in the 1980s, dealing with things like noise and interesting ways of handling continuous features. What to do if you have missing labels? What to do if you have missing features? What if your real value? What if you want to make non-axis parallel splits? The example that we saw for real features was we had only axis parallel splits. How do we get non-axis parallel splits and learn them and so on? In the 90s, the ID3 algorithm was improved, shall we say, was made more robust into C4.5 and C5, and these things are now part of standard packages that we have. The other interesting thing that came about with decision trees is in the 2000s, early 2000s maybe, and late 90s, actually late 90s, one might say, this idea of boosting or bagging became a big deal. And we'll talk about boosting and bagging somewhere in the middle of the semester, but the short version is we have not one tree, but we have multiple. We learn a committee of multiple predictors, and the final decision is some sort of a consensus between them. And it turns out that boosting and bagging, or this is generally called ensembles. Ensembles of decision trees are very good general purpose classifiers that are quite robust with real data. And in fact, as recently as about 2007 or 8, ensembles of decision trees were considered to be one of the best things you can do. If you have new data that you are not thinking and you don't really want to think too hard about designing classifiers. So this is like a very brief one slide summary of the history. If you're interested, you should check out Tom Mitchell's book, the chapter on decision tree. And this lecture is following that chapter. In fact, the example that we look at next to introduce the decision tree algorithm is from Mitchell. It involves deciding whether or not I should play tennis today. And to answer this question, we'll use 4 features. We have the outlook, the weather outlook, whether it's sunny or it's overcast or whether it's rainy. We can measure the temperature and pick 3 categories: hot, mild, and cool. We measure the humidity, high, normal, low, and the wind, strong or weak. And this is a binary classification problem. Will I play tennis today? Yes or no? Yes is plus, no is minus. So given these features, the first thing to do is, of course, to collect data. Let's say I observed my habits for 14 days and collected these 14 examples. We'll be looking at this table a lot, so let me just talk about the notation here. I've abbreviated the 4 features in the columns here. The label is this column here, play or not. And the feature values, I'm just using the first letter. So for example, this means, in fact, the entire row means the temperature is sunny. The outlook is sunny, the temperature is cool, the humidity is normal, and the wind is weak. And on this day, the label is yes, I will play tennis that day. I did play tennis that day. So now the question is, how do our goal is we want to build a decision tree for this data. The basic algorithm, and there are many variants of this, but the basic algorithm, which we will see in some detail, takes all the data and processes it as a single batch. And it recursively builds the tree from the top to the bottom. So this is the tree that will eventually construct. And the algorithm that we'll see is going to build this tree. In order to build this tree, let's break this down into what are the things that we need to know how to do, or what our algorithm needs to know how to do. First, it needs to decide which attribute or which feature should go at the top. Once it decides which feature goes at the top, it can at least start the process of building a tree. Then it needs to decide what to do for every branch of the feature. So outlook can either be sunny or overcast or rain. In each case, what should the algorithm do? So there are really 2 high-level strategies, that high-level questions that the tree learner should answer. It needs to pick an attribute, and then once it goes down this path, it needs to know what to do next. So let's, given that perspective, let's now look at the algorithm step by step. The algorithm is called ID3, and it takes as input the entire set of examples that we have and the list of features that are available at this point. And when I say example, S includes something like the rows of this table here, and it also includes the label. Every row has a label. So let's start. First of all, let's consider all the easy cases first. Suppose you have a situation where all the examples that go into ID3 have the same label. If all the examples have the same label, then you don't need to look at the rest of the features. These attributes are unnecessary because the label is known. So you return a single node with just the label. This is the easy case. And the tree is really a degenerate tree with a single label. If all the examples are plus, then you have a node called plus. It doesn't matter. And when the way to label, this is a trivial tree. The way to label with this tree is this tree here. When a new example is presented, will ignore all the features and just say plus. So that's the easy case. If all the examples have the same label, you return a single node with the label. Let's consider the other case. Otherwise, we need to actually build a tree. So the nice thing about a tree is that it's a recursive data structure. To build a tree, we need to create a root. And this is where we are answering the first question, deciding what attribute goes on top. We create the root, and this is the root that we'll eventually return. And then in between here, we will construct the rest of the tree. First, we need to know which attribute goes into the root. And for that, let's say we have some way, we'll talk about this later. Let's say we have some way of identifying which attribute in this list of attributes best classifies the data. This is the feature A. So what we do then is we, inside this root node that we have created, we put the value of A. A might take multiple possible values. So the feature A might take multiple possible values. Let's say we have different values V. So you have the root A, and then let's say we have different values it can take, and let's say this value is V. Now we need to start thinking about what to do next. For each value that this thing takes, we need to figure out what to do. We first create a branch for each value. And for every value that the thing takes, you create a branch. That's the value that's now the path that we consider. This means that now let's consider what happens under this. Under this, we only need to deal with examples where the feature A takes the value V. So we can call that subset S sub V. So all examples in the original data set where the feature A takes the value V is called S sub V. Now, let's say that this subset is empty. This was like the green triangles that we saw. If this subset is empty, then there is no example in the training set where feature A takes the value V. What can we do? The right thing to do is we should add a leaf node with the most common label in the entire data set. We don't let that branch go without a label. Instead, we just add the most common value the most common label that this can take. So for example, if you have A, and by the way, we'll see an example, we'll work through an example of this process as we go along. So if I have taken the feature A and there's a value V, and at this point, there is no example here. What we do then is we look at the original set of examples, and let's say the most common label there was plus, we just say plus. This is like the green triangles case. If the most common label for green triangles was B, we would have just said B. So for not green triangles, but if the most common label for that particular feature value was B, we would have just said B. Now, the question that I want to pose to the class is, why would we do this? Other than this kind of answers the question I think Anthony asked a little while ago. What is the motivation for adding such a label, even though there is no example with this label? There's no example with this particular feature. And there's a suggestion that you'd be correct most often with this approach on unseen examples. Why? Why would you be correct most often? In some sense, both these answers are the other answer here is you take the highest probability, so kind of make a guess here. That's right. You're making a guess here. You're guessing that, sure, in this particular set of examples that I have, I never saw feature A take value V. However, among all the examples that existed, the most possible value is the one that the most common one is I'm more likely to be right if I take the more common label. This is an example of making the learning algorithm making a decision in order to generalize at test time. Essentially, the learning algorithm does not have any information about this cluster, an example where A takes the value V. It doesn't have any evidence that the labels are plus or a minus. It just takes a guess, and it takes a guess that at that point, the safe guess is to take the more common label, because at least you'll be right more often than not. And the suggestion that there are a few edge cases you have to deal with. If both labels are equally likely, let's say you have 10 examples inside S, and you have 5 pluses and 5 minuses, you just take the most you toss a coin because that's pretty much all you have. You pick randomly, you just say plus. And oh, there's another question. Is it the most common overall? No, it's the most common in the subset of examples inside S that you have seen so far, in the nearest branch, let's say. Now let's consider the other case. The other case is SV is not empty. So then we are here. This means we have some set of examples where, maybe this is too small. We have some set of examples where feature A takes the value V. I'm writing this as a table, but maybe there are other features. And then you have label, maybe plus and maybe a minus here. Now, what do we do next? We have this subset, and this is where the algorithm gets interesting. We have a set of examples, this here, this is S3. We have a set of examples, and we want to build a tree. Because remember, a subtree is also a tree. So we have A here, and then we need to build some tree below that. This is also a tree. What do we need? We need an algorithm that can take a set of examples and produce a tree. It happens that we have such an algorithm. ID3 is such an algorithm. It can take any set of examples and produce a tree. Who said that it has to take the entire data set? It could take this subset and construct a tree using only the remaining attributes, because A is already done. So I can now make a recursive call to ID3 with only the subset of examples. This subset goes in here, and all the other examples go in here. And I don't know what, I mean, this is the cool thing about recursive algorithms, right? You don't care what it does internally. Well, you know what it does internally. It's doing all the stuff that's on the slide, but essentially you're passing off the job to another copy of the same algorithm using a subset of the data and saying, yeah, you take the rest of the data, give me a tree, and I'm going to attach it here. And you keep doing this, and you're done. This is essentially a recursive algorithm that builds the tree from the top down. Any questions before we start now teasing this apart and actually see an example of this algorithm working? So there is one question. What is the attribute that best classifies S? In theory, everything here is everything is actually well defined. There's this one tiny thing here which seems like you can't implement it. Everything else seems fairly straightforward if you're comfortable with implementing this. By the way, you'll be implementing this for your homework, so you will have to get comfortable with this, whether you like it or not. But the one thing that is not defined is the attribute that best classifies the example. This is the key question. This is the question that tells us what should go into the root, what attribute is at the root. And that's a good segue into the next thing that we are going to look at. We need to pick the root attribute. And the goal, and this is where we are going to introduce what's called an inductive bias. We'll talk about inductive biases as we go along, but every learning algorithm has an inductive bias. Every learning algorithm has some preference that it introduces. And the hope is that this preference, the preference over the hypothesis space, the hope is that this preference that it introduces is somehow meaningful. The inductive bias that we're going to try to capture is to make the decision tree as small as possible. We want smaller trees rather than bigger trees. So the idea is the following. Imagine that you have a data set where you have two trees, both of which can perfectly capture the entire data. One tree, using some feature, has only one node. Let's say that you have one that takes something like this. This is one tree. Another tree is something that is, it doesn't use x1 at all. It uses x2, and then it goes down. Here it uses X3, and maybe here it uses X4 here, and it keeps going down all the way. And the height of the tree, let's say, is 100 nodes. The height of this is just 1. The intuition that we want to capture with the decision tree learner is we prefer smaller trees to larger trees. And this is an example of Occam's razor. If you think of trees as an explanation of the data, Occam's razor says among multiple explanations, prefer the one that's the simplest. For a decision tree, a natural definition of simple is size. So we want the simplest explanation that is consistent with the data, because this is almost a philosophical point. If you have multiple explanations that are all consistent with the data, simpler explanations that are consistent with a lot of data have a higher likelihood of being true. How do you know this? This is not an obvious question. This is not an obvious answer, but it's been the basis in some sense of scientific inquiry forever. Among multiple explanations that all of which perfectly capture nature, you prefer the easier one. You prefer the one that's simpler. If you want a nice something to think about why this is true, and convince yourself that this is something that we intuitively or more explicitly have been doing in science forever. And this is what we are trying to do with decision trees. This is what we'll try to do as we go along with every learning algorithm. You can think of learning algorithm as searching for explanations of data. And one way or another, we want to find the simplest explanation. Now, the problem is actually it's a computational problem. If you can enumerate every possible decision tree that is consistent with the data, and then find the one that is the smallest, life would be easy, except finding the minimal consistent decision tree is intractable. And once again, my screen share has decided to stop working. So let me try this again. Finding the minimum consistent decision tree is intractable. It's NP hard. Most of you have a majority of you in the class have a computer science background, so you probably have seen NP hard before. If you're not from a computer science background, don't worry about it. We'll not get into too much details. It's just computationally intractable. So we want the decision trees to be small. That's a clarification. Should we want the decision trees to be small in terms of depth or in terms of the number of branches? Usually when we say small, we mean depth. So what this means is that exploring the set of all consistent decision trees is computationally not feasible. So we can't do it. Instead, the recursive algorithm that we just saw is a heuristic. And by choosing the root attribute in certain ways, we might impose a preference for simpler trees, for smaller trees. The heuristic that we will look at does not guarantee optimality, because if it could guarantee optimality, then we would have solved an NP hard problem in computation, in polynomial time. So we're not doing that. There's no guarantee of optimality, but there's a preference for simpler trees. And all of this preference is encoded in the one thing that we have to choose, namely, how do we pick the best root attribute? How do we pick the root of the decision tree? And this is, to kind of give you an intuition for why this might be, or how this might work. Let's consider a simple case where we have two features, A and B. And let's say we have this data set with 200 examples. When A is 0 and B is 0, the label is minus. And somehow we have seen this exact example repeated 50 times in the day. Similarly, we have seen A is 1 and B is 1 with a label plus We have seen this example 100 times. We have never seen this example. When A is 1 and B is 0, just so happens that our data does not have any examples of this kind. Now, let's build a decision tree for this. For that, we need to decide which attribute we should select. Thankfully, we have only 2 attributes, so we can actually build both the trees and see what happens. If you split on A, when A is a 1, the labels are plus, and when A is a 0, the labels are minus. Here. So we get what we are going to call a purely labeled node. So this, if you split on this, you essentially directly get to the label. When you split on B, when B is 0, here and here, the labels are minus. But when B is a 1, here and here, you still have some examples to deal with. You haven't yet completed the decision. We have to still split on an A to decide whether we are in this bucket or this bucket here. So the question is, which of these is preferable? And don't just use the everything I said about smaller trees. Think about why you might want to pick one or the other route. So I've just launched a poll and ask yourself, which of these 2 trees would you prefer? And I'm not asking you why, but think about the why. While you answer the poll, let's say there's a question. What are the practical consequences of larger decision trees? Slower inference, lower accuracy, and so on. So slower inference is true because you have to go through more steps, but I don't think that's a huge deal. Essentially, by inference, it's prediction. Prediction is going to be just, given an example, you're going to traverse down only one of the paths. So the question we should always ask ourselves right now is generalization. Which of these 2 things would lead to better generalization? There's another question. There's a clarification. Why don't we split on B afterwards when we start with A as a node? This is an important question because let's take the case where we have split. I'm going to draw the tree for that. Let's say we have A. I can go to either A is a 1 or A is a 0. So let's consider all the cases when A is 1. When A is 1, you have this row and this row. But look, there are no examples when A is 1 and B is 0. So the only examples that we have when A is 1 is this particular row. So we don't need to split on B. When A is 1, the label is plus. Because remember, in the ID3 algorithm, this is the base case. If all examples have the same label, you return a single node with that label. So when A is 1, we are essentially in the base case because in this bucket, all examples have the same label. All 100 examples are a plus, so we can just say plus. Otherwise, we are when A is 0, we are here. But look, again, all examples have the same label. So we don't even have to worry about B. We just pick the label and we move on. So when we split on A, we have essentially separated out the examples into 2 plus or minus. There's no reason to look at a B because looking at A, we knew what the label was. I hope that answers your question, Dan Paul. There's another question. If you knew the true decision tree, could we think of this in terms of edit distance? Sure. If you knew the true decision tree, you can think of this as in terms of edit distance, or you can think of it in terms of a simpler version, which is the true tree, does it have the same label at the root? Effectively, it is the edit distance. It's actually, you can think of it as not the string edit distance, but what's called the tree edit distance. And I will let you think about that offline. All right, let me end the poll. And it seems like 70% of you think that there's a preference for this tree, and a smaller subset, 30% of you, have a preference for splitting on B. Now, can someone who suggested that we should split on B make an argument for why that's a better choice? So why would you, so there's 30% of you who split, who suggest that a better attribute to split on is B. So why would that be?
Yeah, I just think it would generalize better potentially, because those 100 examples aren't. I don't know. I feel like the tree for A just seems a bit simplistic, even with just the examples we have. But it doesn't seem like it would generalize well.
Okay, so let me offer you a counterpoint. I would argue. So this is really an important thing. So let me spend a little bit of time on this. So the proposal was the tree on the left would generalize better because it's looking at more information. Maybe that's the intuition. There's another. The intuition might be like, look, the tree on the right is not even looking at all the features. It's just looking at A and not even looking at the full example and making a decision. So maybe in the future, it might preemptively get the label without looking at B. My counter argument is there are, there's another comment. In the future, if we get A examples from A equals 1 and B equals 0, the tree for A would still hold. I have to first verify if that's correct. Actually, if we get examples of that kind, this tree would actually make a mistake because the label is a minus. In fact, that's the reason that particular row was chosen. So I would argue that this is really a point of contention, right? If that is the case, what if those examples were actually never going to happen in nature? Then this particular tree might actually be better because a deeper tree like this one might actually be fitting the noise in the data. You're assuming that your data is all perfect. But remember that data might have noise. So a deeper tree might actually be finding little corners of the data space where it's just splitting on extra features that are really irrelevant. The tree with, that splits with an A is making a decision that is almost going to be right, and it's a simpler decision. This is really an inductive bias that the most learning algorithms are going to want to have. Most learning algorithms have to work using only the examples that we have, that it gets to see. This learning algorithm that we are trying to work with can only see these examples. And the most common kind of a inductive bias, the most common kind of a assumption that most learning algorithms have is that the future will look like the past. In the past, we saw 0 examples of this where A is 1 and B is 0. In the future, we may not see too many examples of that kind. So why should we bother splitting on B? Because we may not even encounter these examples. And this, if we never encounter that, why should we even care about the fact that the labels are minus? So this is a intuitive argument. This is not a formal argument. The intuition here is that there is a preference for the simpler trees simply because a simpler explanation that perfectly fits the data could not be an accident. This is the intuition. If you have a lot of data and you have 2 explanations that both of which perfectly, 2 rules that perfectly explain the data, and one of them is much smaller than the other. If you have a lot of data, it could not be an accident that a simple rule explains the data. So there must be a fundamental truth to it. This is the intuition that we are trying to capture. And that's the reason why most learning algorithms would prefer going with A here. But let's actually make this a little bit more complicated. All of this argument that I said was hinged on the fact that there were 0 examples here. What if, instead of 0, we saw 3 examples? In this case, the tree for B is basically the same, but the tree for A now starts looking, essentially they are structurally identical, with different labels, with different elements in the nodes. The tree for B was exactly the same, but the tree for A, after going down this path, when A is a 1, we still have to split again on a B to decide whether A is 1 or whether the label is a plus or a minus. Convince yourself that these two things are exactly the same function in all cases. Even it doesn't matter whether A is the root or B is the root. But now we still have to decide which one is better. These two trees are structurally similar, but let me make the decision a little bit more easy by adding the number of examples that come down each path. When A is a 0, we are in this block. So there are 100 examples that go here. When B is a 0, there are 53 examples. That's really, when B is a 0, it is this and this. So there are 53 examples that go down this path. So if I choose an A, in 100 out of 100 and 203 examples, that's almost half the examples, we immediately get the label. If I go this way, in only 1/4 of the examples am I getting the label. I still have made, unresolved uncertainty on 3/4 of the examples here and only about half the examples here. So the goal of the ID3 algorithm is to try to resolve any remaining uncertainty as high up the tree as possible so that we can quickly get to the label. That way, we are not left with more and more splits of the data, because at that point, we might be fitting the noise. Maybe these 3 examples were just noise and should never happen. Should we aim for a balanced tree? It doesn't have to be balanced. It should be short. Is the goal. It doesn't really have to be balanced. Here's a very short tree that is not balanced. It uses 3 features. Yeah, short equals depth. So the depth of this is 3. So this is, I'm arguing here that even in this case, the advantage is for A, because in most examples, in a majority of the, not majority, but in a larger fraction of the examples, the uncertainty is resolved in one step. So how do we quantify this? And this is really the main point of the ID3 algorithm. So once again, the goal is to have a decision tree that is as small as possible as per depth. This is according to depth. And the only thing that we can do to control the depth is to decide which attribute we are going to use to split the data. And the intuition that the ID3 algorithm tries to capture is we want to split examples to subsets. We want to split the examples to subsets that are as relatively pure in one label as possible. That way, we are closer to the decision for more examples. How do we do that? The ID3 algorithm uses this heuristic called information gain that goes back to Quinlan's original work. Let's see what information gain is. But in order to introduce information gain, I need to take a short detour through a brief introduction of the idea of entropy. I remember not all of you have encountered entropy before. So I'm going to just give you a high-level overview of this concept, introduce you to what entropy is, and then we'll build this information gain heuristic, plug it into ID3, and see what happens. So I'm going to introduce entropy using this particular situation where we have a set of examples, but it's a broader concept that actually has its own fascinating history. So for us, given a set of examples, each example can be a plus or a minus. Let's say the fraction of examples that are plus is P1, and the fraction of examples that are labeled minus is P minus. The entropy of this set with respect to the label is defined to be minus P plus times log P plus minus P minus log P minus. Now, if you're like me, just looking at an equation means nothing. So let's see what it actually means. But let me just make this a little bit more complicated. If you have k possible labels, the entropy of this probability distribution with k categories is the sum over all the labels, pi log pi. And all the logarithms here are log to the base 2. All the logs that you will use in your homework are also log to the base 2. Let's see what this means. First, let's consider the case when all examples belong to the same category. When all examples belong to the same category, let's say plus, then P plus is 1 and P minus is 0. P plus log P plus is, let's literally just plug this in. So there's a short question. When selecting the root, do we analyze the data by looking at it, or do we create decision trees by? No, this is a greedy process. We select one root and move on. We don't consider multiple trees. It's in the choice of the root that we consider multiple roots. And then once we make a decision, we just continue with it. We don't go back. There's no backtracking. So when P plus is 1 and P minus is 0, this becomes 1 times log 1 minus of this minus 0 times log 0. Now log 0 is not defined. 0 log 0 is an indeterminate form, and it conventionalized to take the value 0. Log 1 is 0, so this also takes the value 0. So the whole thing, the entropy is 0 when all examples belong to the same category. Now let's consider the case when all examples, there are 50% of the examples are plus and 50% of the examples are minus. So when P plus is half and the P minus is half, so we have minus half log 2 to the base half minus half log 2 to the base, log half to the base 2. This quantity here is exactly 1, or actually it's minus 1. So this is minus 1 and this is also minus 1. So you have half plus half, which is equal to 1. So the entropy when the examples are equally distributed is 1. The entropy when the examples are all in the same category is 0. In some sense, yeah, so you can take the limit of, so to handle the case with log 0, you take the limits basically. So entropy has the way to interpret entropy is how many bits of information are required on average to encode information. How many bits are needed to encode information, in this case about the label. When the probability of plus is a half, then 1 bit of information is needed on average. If the probability is more, then on an average, we need to send less information because more often the thing is going to be positive or the label is plus. Let me give you a more intuitive example. I think this might be from Russell and Norwich's textbook. Suppose I'm sitting in a weather station and I need to give information about the weather. Let's make it a binary decision. Is it snowing or is it not snowing? Or is it cold or not? Is the temperature below, say, freezing or not? Now, depending on where the weather station is, this information is obvious or it's not. So let's say I have to convey this information to you, and let's say I'm sitting in Salt Lake City. And depending on what time of the year this is, this could either be true or false. It's cold or it's not. And you don't know upfront whether it's cold or not. So I actually have to convey this information. Now, let's say instead of that, we are sitting somewhere. Let's say we are in the Amazon rainforest. And then I can ask, is it below freezing or not? You can ask me that question, but you don't need to. You already know that information. There's no reason for me to convey that information to you. So the number of bits of information that I need to send to you is definitely less than 1. Whereas in Salt Lake City, depending on what time of the year you ask me the question, you still have that uncertainty. So there is, I need to send you some information in Salt Lake City about the weather, but in the Amazon, I don't need to. I think if you think of, you can think of other places where this information is obviously unnecessary. There's no reason for you to ask this information. For example, in Antarctica, it's cold. I've never been there, but I assume even summer in Antarctica is cold. So there's no reason to ask whether it's cold. Yes, the answer is cold. So that's the case where one label, cold, dominates the conversation. So let me, while I'm rebooting my screen share for the 4th time, I think today, let me just, you should probably think of questions. Okay, that was too quick for you to think of questions. So let's, what's the interpretation of entropy? If one label is far more common than the other, this blue bar here is representing the entropy. If one label is far more common than the other, then the entropy is low. If both labels are equally likely, then the entropy is high. The uniform distribution, irrespective of whether we have 2 labels or more labels, or whether it's a continuous probability, the continuous random variable, the uniform distribution is the one that has the highest entropy. So the uniform distribution will have the highest entropy, and the distribution where one label is more common. By the way, these pictures, these are the labels, and this is the probability of labels. Here. So, and the blue bar is the entropy. So if the uniform distribution characterizes the situation where we don't know which of these things is happening because all of them are equally likely. Whereas in this case here, one label, the circled one, is far more likely to happen than the other. And that's why the entropy here is low. The uniform distribution, the uncertainty is high and the entropy is high. So that's the high level interpretation of entropy. High entropy characterizes high uncertainty. Low entropy characterizes low uncertainty. In the context of our decision trees, low uncertainty in the label is what we want to resolve early on. So we want to find the attribute that very quickly removes as much uncertainty about the label as possible so that we don't have to grow the tree long. So the intuition of the ID3 algorithm is to find an attribute that reduces the label entropy the most. Among all the features that are there, among all the label attributes that are there, you find the one that reduces the entropy in the labels the most. And that one is going to have a preference for creating shorter trees. While before I go on, are there any questions? Doesn't seem like I can't see if someone's typing, so I'm going to move on, and if there's questions, I'll come back. The intuition is we want to find that feature. We want to, so what ID3 is doing is at every step, it is ranking all the attributes, and we want to find at any point the node that reduces the entropy the most. So this is our scoring function. So you can think of it as a function that scores every feature according to some quality and picks the one that has the highest score. And the scoring function is going to be the one that we'll see in a bit. It's called information gain. It's how much entropy would this remove? And so there's a question. The next node, will it be the attribute that reduces the entropy the second best? Not quite. The next node, as per ID3, is remember, it's a recursive call. So each part of the tree, so let me go back to the algorithm. The next node is going to be decided here. It's an independent call to ID3. So each subset, once again, in the subset of examples, you find the one that reduces the entropy the most. Once we compute the entropy at the top, we discard that feature, and then we consider the subset of the data here and find once again, we find the best feature. And in other words, it's the one that reduces the entropy the most in the subset of the data. It may just happen to be the second best, but it doesn't have to be, because after you split on this feature, maybe you don't need any more splits, for example. So let's now, in the 4 minutes that are left, I'm going to talk about information gain, and then I'll continue this in the next lecture again. The information gain of an attribute, this is the property that we will use to rank attributes, is the expected reduction of entropy that you get by splitting the data according to this attribute. So what you do first, so we are given a data set S and an attribute A, and we want to consider how good is this attribute. What you do is you first find the entropy of the entire data that we have. And then we ask, for every partition, so you have an attribute A, and let's say you have partitioned it into 3, let's call this as V1, V2, and V3. And here we have a subset of the examples, right? Now, let's say we have 30% here, say 20% here, and 50% here. Now, for each subset, we can still compute the entropy of the subset. And the reduction in entropy is the entropy of the data at the top minus the average entropy of these partitions. And this average is weighted by the fraction of examples that it represents. So this would be here 0.3 for the first one. This is 0.3, this SV divided by S. And for the second one, it is 0.2. And for the third one, it is 0.5. And we compute the entropy of each partition. And the difference is what is the entropy that is left behind after we make a split on A. So the entropy of the partitions are calculated by weighting this thing inside the summation. Every partition is weighted by how many examples are inside that set. The entropy of that partition is weighted by that, because if you have a partition which has only one example here, let's say this was really, really small. So instead of 20%, let's say this is 1% of the data, and this is 49% of the data. This is just one row. Then this partition is less important because it, sure, it may have a very high entropy, but because it is really small, we care more about these partitions because they are more common, and so they will be weighted higher according to this criteria. So partitions with lower entropy will lead to higher gain because this quantity is high, this quantity is low, so the gain is higher. So if we manage to split the data so that each subset of the data has very low entropy, in the best case, 0 entropy, then the gain is all the entropy of the data, all the uncertainty of the data. Whenever you hear entropy in your mind, replace it with uncertainty. If the uncertainty after splitting is low, but uncertainty before splitting was high, that means the gain is going to be high as per this definition. Now, once you have this, I want you to go back and check whether which of the splits, A or B, in the example that we saw, would be preferred. And the intuition that you should always keep in mind is higher entropy is high uncertainty, low entropy is low uncertainty, and we want to remove uncertainty. We want to pick an attribute that removes as much of the uncertainty as possible. So what you do offline is among the two attributes A and B that we saw in the example, actually work through this thing and see which of these attributes has higher information gain, which of these will remove the uncertainty more. All right, we should stop. It's 10:30 now. So the next lecture, what I'm going to do is I want you to kind of just briefly refresh this before the next lecture, because in the next lecture, I'm going to actually step through the algorithm using the tennis data and in the class build a tree so that you see this algorithm in being executed, so to speak. And we're going to step through this process, compute the information gain, and see what kind of attribute it prefers. If you want to kind of preempt what I will do, do it on your own offline, and we can compare notes. All right, I'll stop now. maybe there's time for one question because we are at 10:30, so I don't want to keep people here. So if you want to leave, feel free. I'll take maybe one question. Okay, we are actually out of time, so I shouldn't keep you here longer than necessary. If you have any questions, come back on Tuesday and we'll start from here. We'll go through the algorithm. I'll see you all on Tuesday. Thanks.